So let's get started. Today we're looking at Chapter 10, which is on hypothesis testing. And this will just be a kind of a summary of the process. And don't forget tomorrow that we're going over... Oh, good morning, Jerry. We're going over tomorrow at 9 a.m. We'll review for the final. You don't have to be there live if you're not able to, but I do recommend you watch it. You may have noticed I already uploaded the key to the review for anyone in particular that's taking the final tomorrow. Anyway, yeah, so let's get to work on Chapter 10. Regrettably, we don't have more time to go over hypothesis testing because, honestly, I would like to spend 2 or 3 days going over it at least. Well, 2 or 3 days I think would be good. But anyway, we're at this point now, so can't help it. So, let's talk about a statistical hypothesis first. One of the things that you may notice as we go through this is there's a lot of similarities with confidence intervals that we just looked at prior to the test on Chapter 9. And the theory behind it is basically the same. It's just we're working towards it from kind of a different direction now. And the idea with the statistical hypothesis is this is a claim or statement about a population parameter which, when we say population parameter, we could be talking about the mean, the standard deviation, or a proportion. We are just going to focus on the mean today. I think that'll be the most helpful of the three to talk about, because there is one question on the final regarding the hypothesis test about the population mean. And this may or may not be true, this claim that we make. But the idea of the hypothesis test is to determine whether or not this claim that we make is true. All right. So, when we say we're making a claim or statement about a population parameter, I'll just refer to the mean here, henceforth. The idea is that that we have some kind of established value for something, like we understand that the average IQ is 100. The way that the IQ scale is measured. We understand that the average lifespan of Americans is like 78 or 80, something like that. Things like that. Things that have been well established based on research over years, multiple different research projects or papers or whatever, and these are established in their field. And so our purpose here with hypothesis test is that we have, let's suppose that we've done some new data collection ourselves, and we've come up with a very different value for this population mean, or from our sample mean, I guess I would say. Our sample mean comes up very different than the population mean. It doesn't have to be very different, it could just be a little bit different, but it may be enough to challenge this long-held value. Like maybe things are changing so that we have this different result. And so that's the essence of hypothesis test is how can we go through and determine if we have enough data to say that this previously held population mean has changed. You know, what if we do some research and it says that people are getting married later and later in life? Okay, so if the average age of marriage is previously known to be 25, I don't know what the number is. At first marriage, I guess we should specify. And but we've done some data collection, and we find that that's closer to 26 now, which that's actually significant. A 1 year difference. I know it's kind of weird to think that, but that's a significant jump. Then we can use this method of hypothesis testing to challenge that value and see if we have enough data to say that yes, we're not to say yes, it has changed. Now, the important thing to mention here is that we're not saying, if we've done this research, we're not saying that the average age is now 26. We're saying that we just don't think it's 25 anymore. We think it's increased. Okay, so it's important to note that we're not trying to establish a new standard. We're just saying that the old standard has changed, and that's really the essence here. Is we're challenging the old result. We're not trying to present a new result. Okay, that takes a lot more research and a lot more data to really establish a new benchmark. Okay. All right. I feel like I mess with the camera angle here all the time. I keep bumping it, I think. Anyway, let's look at the basics of a hypothesis test, which is our hypothesis statements. Anytime we start a hypothesis test, these are the first two things that we have to address. So one, we have what's called the null hypothesis. And the null hypothesis, this is written as H with a subscript of 0. Now, the way that we pronounce that, generally speaking, in statistics, is H naught. Naught being more of a traditional British word for 0 than necessarily American. But actually, we use that pretty widespread in mathematics. Whenever we have a subscript of 0, we'll call it H naught or Y naught or etc. Not try to be ironic saying why not. Anyway, so we want to state a null hypothesis. Now, the null hypothesis is a statement that expresses what's currently held to be true about a certain parameter. a population parameter. And for H naught, we might say, for example, our statement might be mu is equal to 25. Or we might say our proportion P is equal to 0.75. Just some statement about what is previously known to be true based on years of research or data collection, etc. So this is exactly how we write it. We say H naught colon and then mu is equal to, or P is equal to, or sigma is equal to whichever parameter we're testing. As I said, we're focusing on the mean, so we'll use mu equals 25 or whatever the value is. So that's our null hypothesis. Now, the other one we look at is called the alternative hypothesis. And the alternative hypothesis puts forth, or it's a statement that really describes how we think a parameter has changed based on our new data. Okay. Now, it's important to note here, when we express the alternative hypothesis, we actually use the exact same value from the null hypothesis. Let me make that a note here. Also, alternative hypothesis is H1. I should have mentioned that also already. So we have H naught and H1 are null and our alternative hypothesis respectively. So as an example, H1 could be written as previously we said mu was I think on the previous page I said 25. So we may say, okay, mu, we think that's greater than 25 now. Or we might say, okay, our population proportion P, maybe that's now less than 0.75. Okay? So we have the original value from the null hypothesis, but now we say it's either greater than or less than what was previously held to be true. We could also say not equal to, although that one's a little more complicated. We're just going to focus on these two scenarios for today. Okay. I was going to try to do a lot of the work on calculator, but it turns out that only the bigger graphing calculators can do hypothesis tests. The 36 cannot, so that's unfortunate. But so I'm gonna we'll just do it the old-fashioned way on this one. So it's not terrible. It's just a little bit more to remember. And that's really the issue here. But let me outline this process of classical hypothesis testing. I feel like there's something else I need to cover first. Hang on. Oh, yes, there absolutely is something else I need to cover before I get to classical hypothesis testing. Okay, so continuing. Let's look at the conclusions that we may draw and some of the associated things that we'll need to talk about there. There's really two conclusions we can draw. One, we may choose to reject H naught, which means we have enough data to say that the parameter has changed. And two, we may choose to fail to reject H naught, which means we have insufficient data to say that the parameter has changed. Okay. Now, it's important to note the wording here. So reject H naught, okay, that means that we have demonstrated that we have enough data to say that this parameter is now different than what it was previously thought to be. The wording on the second one is most important, that we fail to reject H naught. We don't want to take away from the fact that we have hard data that tells us that we got a different value for this mean that, from the parameter. Okay? I mean, that still happened regardless. It's not that our data wasn't good. What we've actually proven is that while we did get a different value for the mean, it's within the realm of possibility as far as standard deviation and sample size are concerned that we could have gotten this result from a normal population. That with that original parameter still in effect. So essentially it means we either don't have enough data or our data is a little bit too skewed towards outliers or something like that. Now, So the reasoning there is that everything we're doing here is in regards to H naught. We're not trying to prove H1. We're trying to prove or disprove, or we're either trying to reject or not reject H naught. Okay. Now, there are some errors that we make here because we're not doing this with 100% confidence. It's impossible to do any testing with 100% confidence. So we have two types of errors. Let me go ahead and go to the next page for this one. We have a type 1 error. And this is if we were to reject H naught when H naught is actually true. And kind of the analog we like to use for this is it could be like we have if we were to convict an innocent person. So it's like H naught is innocent, but we've chosen to reject it. Okay. A type 2 error. This is when we fail to reject H naught when, in fact, we should reject it, when H1 is actually true. And kind of the way that we can describe this is as if we set a guilty person free. Okay? Both of them would be bad things. We wouldn't want to convict an innocent person. We wouldn't want to set a guilty person free. But, you know, depending on evidence, depending on other factors, it may and it does happen. Both scenarios. But we really don't want to make those types of errors, either one. Now, we have what's called the level of significance, which is one thing that does affect how our hypothesis test works. Level of significance this is the maximum probability of making a type 1 error that we're comfortable with in a hypothesis test. Okay. And for this level of significance, we typically use, and it's important to note that we use alpha to represent the level of significance. Alpha being the first letter of the Greek alphabet. If we haven't used it before already, I feel like we have. Yeah, because we used Z alpha over 2 and T alpha over 2 in chapter 9, at the very least. Typically, we use alpha equals either 0.01, 0.05, or 0.1. Okay. Now alpha equals 0.1. This basically corresponds to 99% confidence. Alpha equals 0.05 is basically 95% confidence. And alpha equals 0.1 is basically 90% confidence. That's kind of the comparison we can make to confidence intervals. So this alpha level is basically 1 minus alpha is our level of confidence. And I think I mentioned that specifically back in chapter 9. It's been a week, so I don't remember. 2 weeks. Anyway. So we have this alpha value. Now, Now we can look at our classical approach to hypothesis testing. And this is kind of the steps that we need to take in a hypothesis test, and it outlines specific values we need to find and compare things to. I'm going to start on a fresh sheet of paper here. Okay, first step in classical hypothesis testing is that we state our null hypotheses and our alternative hypothesis. So we state H0 and H1. That's any hypothesis test. We always start off with that. Second, we find our critical value based on H1 and alpha. Find our critical value based on H1 and alpha. Okay. So if H1 states that it's greater than the parameter, we call this a right-tailed test. And if H1 is less than the parameter, this is a left-tailed test. Okay. So if we have a right-tailed test, looking at our normal curve, that means that there's some critical value z is our critical value, where the area to the right of this value is equal to alpha, which is our level of significance. Now, sorry about that. Alpha is equal to, so, not alpha. Yes, alpha. Sorry. Bouncing around here. Alpha equals 0.1 would tell us that z is equal to 2.33. Alpha equals 0.05 would tell us that z is equal to 1.645, and alpha equals 0.1 would tell us that z is equal to 1.28. So depending on which level of significance we're using, we can tell what our z is going to be based on that. Okay. Now, if we have a left tail, okay, then we have a critical value z over here on the left, where the area to the left is alpha. In this case, if alpha is 0.01, then our critical value z is negative 2.33. Alpha equals 0.05 means our critical value z will be negative 1.645. basically it just flips all these values to negatives when we look at the opposite side. The graph is symmetric after all. And so we have z equals negative 1.28 for alpha equals 0.1. So that's our critical points. And so depending on our H1 statement and our value for alpha, we can choose the appropriate z to represent our critical value. Okay, 3. Well, I'm going to run out of room here. I want to try to finish on the same page. Maybe I should have done more. Yeah, that's fine. So our third step is calculate our test statistic. Which says ZT is equal to square root of n times x bar minus mu over sigma. Now, notice that we have the same formula that we were using back in chapter 8 for z-scores when we have a sample size. So certainly sample size n is going to play a role here, as well as our sample mean. And then we also use our population mean and our population standard deviation. If we don't know the value of sigma, we can just use s here, although if we don't know sigma, then it becomes a little bit more complicated. So I'm just going to focus on working with sigma. Again, something else that we could look at if we have more time, if we had more time. Okay. Now 4, after we calculate ZT, we make a decision. A, we reject H naught if ZT is in the shaded region of the respective normal curve. So basically, for a right tail test, if ZT is greater than our critical value Z, or in the left tail test, if ZT is less than our critical value Z in that shaded region, then we can reject H naught, or B, fail to reject otherwise. Okay. And then our fifth and final step, summarize the results. So just like we did with our confidence intervals, we would like to write just a sentence summarizing what this actually means when we have decided to reject H naught or fail to reject H naught. And what does it tell us about our data, and what does it tell us about the parameter, or just kind of summarizing what we've discovered by this. And that's our classical approach, and it's pretty thorough, and it is somewhat complicated, unfortunately. Now, kind of the shortcut for these critical values. Let me show you how we arrive at those. Let's look at this scenario here, because this is a little bit easier. If we say the area to the left is 0.01, basically we're at the first percentile. And the way that we calculated the first percentile is we did second data We went down to inverse normal, and we did 0.1 with 0 for our mean and 1 for our standard deviation. And that's where we get, 0.1, sorry, that'd be our 10th percentile. So that gives us a value of negative 1.28. So that's where we get that value right there. Now, we can go back and do that with 0.01, and then you can see that's where we get negative 2.33. Okay, and then we can go back and do that with 0.05. And that's where we get negative 1.645. We can do the same for the opposite side, but remember in this case, our inverse normal is a percentile, which basically means the area to the left. So if we want 0.01 to the right, that means there's 0.99 to the left. So we would do the 99th percentile, and that would give us z equals 2.33. For 0.05 to the right, that means there's 0.95 to the left, 95th percentile. That would be 1.645. And then for 0.1 being our area to the right, that means there's 90% of the areas to the left. So 90th percentile, 1.28. So that's how we would arrive at those values if we needed to figure those out. Anyway. So let's look at some examples now. Let's look at some problems. And I'll keep this handy so we can refer back and forth to it. These three examples are from section 10.3 in the book. Let me find them real quick. Let's see, this first one is number 18 on page 502. According to the American Time Use Survey, the typical American spends 154.8 minutes per day watching television. A survey of 50 internet users results in a mean time watching television per day of 128.7 minutes, with a standard deviation of 46.5. Conduct the appropriate test to determine if internet users spend less time watching television at the alpha equals 0.05 level of significance. So we want to write down our key values first before we do anything else. So we know that they told us that the established value for mu is 154.8 minutes. We're also told that we have a sample size of 50, and from that group of 50 we calculated a mean of 128.7 minutes. We know that our sigma, our standard deviation, is 46.5 minutes in this case, so there's some wiggle room. We're calculating this at an alpha equals 0.05 level of significance. So those are the 5 values that we really need to get to be able to work this problem. We need mu, we need n, x bar, sigma, and alpha. So we begin with our hypothesis statements. For H naught, again, we just state what mu is equal to. So mu is equal to 154.8. Now, for our alternative hypothesis, what kind of claim do you think we can make based on our sample mean? Do we think mu is going to be larger or smaller than 154.8? So we look at our X bar and say, hey, from our sample of 50 people, we got a smaller mean here. And it looks a lot smaller. Okay? So our alternative hypothesis is that we think mu is now less than 154.8. Okay? So again, it's based on what we found for X bar and how that compares to mu, whether we say greater than or less than here. Now, because we said less than, that's also going to be a left tail test. Okay. So we look at our normal graph. So we're going to need a critical point Z. We know zero's in the middle. We're going to need a critical point Z for alpha equals 0.05 in the left tail. Now, going off what we said before, for a left tail test, alpha equals 0.05. We'll use Z equals negative 1.645. Okay, so we know that to be true. Okay. Now we calculate our test statistic, ZT. Now remember, ZT is square root of n times X bar minus mu divided by sigma. N, we know it's 50. X bar, we calculated 128.7. Mu is 154.8. And sigma is 46.5. So now we go into our calculator. We say square root of 50, close parentheses, times parentheses 128.7 minus 154.8. And then we divide by 46.5. And so we get a value of 3.97, negative 3.97. Right, and so we graph this on our graph here. So the question is ZT going to be to the left or to the right of Z? Now, Z is at negative 1.645, so negative 3.97 is actually much further to the left. So ZT is in the shaded region. And so then what is our conclusion? Well, if ZT is in the shaded region, we reject H naught. Okay. And that's our decision. Okay. So we've chosen to reject H0. Now we need to make a statement summarizing overall what this has told us. So excuse me. So we can say now that we have sufficient data at the alpha equals 0.05 level of significance to say that the mean amount of television watched by Americans has decreased. Okay. Now, this statement here, again, we will say we either have sufficient data or we do not have sufficient data if we chose to fail to reject at the whatever level alpha that we have, level of significance, and then we address what this tells us about the problem we were looking at, which in this case talking about the mean amount of television watched by Americans, which I left out that part, but it's fine. I left out the by Americans part, but we really should include that because we are specifically looking at Americans. But anyway, we were able to prove that it has decreased. Now, the reality is it probably hasn't decreased. It's just how we're consuming media has changed. That might be a better way of saying it. Between Netflix and similar streaming services and YouTube, even Twitch, and other content sharing websites, how we consume media is now different than it used to be. So it's not that we're just sitting down to watch live television, which is largely true. We don't do that nearly as much, but it has changed how we consume media. That's probably the larger study, and in fact, if we count screen time, probably it's increased rather than decreased. Especially during the pandemic, it's just not been happy times. Okay, but that's how we proceed through that problem. So let's look at another example. This next one is number 13. I don't know why I went in this order. It's okay though. Let me turn back the page. Now 13 says the ACT is a college entrance exam. ACT has determined that a score of 22 on the mathematics portion of the ACT suggests that a student is ready for college-level mathematics. To achieve this goal, ACT recommends that students take a core curriculum of math courses, Algebra 1, Algebra 2, and Geometry. Suppose a random sample of 200 students who completed the core set of courses results in a mean ACT math score of 22.6 and we have a standard deviation of 3.9. Do these results suggest that students who complete the core curriculum are ready for college-level mathematics? That is, are they scoring above 22 on the math portion of the ACT? We want to test this at the alpha equals 0.05 level of significance. So let's go through and look at all of our values. So we've established that the mean score on ACT Math is 22. That's our passing score. We have a sample size of 200 students who've all taken these recommended courses. From our sample, we get a mean ACT score of 22.6, and we have a standard deviation of 3.9. And finally, we want to use alpha equals 0.05 as our level of significance. So that's the information that we have. All right. So we start off with our hypothesis statements. Our null hypothesis, we simply restate mu is equal to 22. And for our alternative hypothesis, are we going to say it's larger or smaller than 22 based on our sample data? Now we look at our x bar that we calculated, or that we were given. And so from this sample of 200 individuals, we have a mean value of 22.6. So what we're saying is now, because we got this value, we think mu is now higher than 22. Instead of 22 being a mean score, we think we're able to do better than that. Now, because it's greater than, that means it's going to be a right tail test. So we look at our graph. So alpha equals 0.05. That means z, our critical value, will be here. And so for alpha equals 0.05, remember if we're on the right tail, we'll use z equals 1.645. Okay. So 1.645 is our critical point. Now we find our test value. Square root of n times x bar minus mu over sigma. So we'll have square root of 200 times 22.6 minus 22, and then divided by 3.9. So we enter that into the calculator. Divide 3.9. And so we get a value of 2.18. So the question is 2.18 going to be in the shaded region? So basically, how does our 2.18 compare to our critical value, 1.645? Well, certainly 2.18 is bigger than 1.645, so ZT 2.18 will be to the right, and it will be in that shaded region. So, our decision then, again, we reject H0 if ZT is in the shaded region, and that's exactly what we can do here. Okay. Now we can write our conclusive statement. So we have sufficient evidence or sufficient data at the alpha equals 0.05 level of significance to say that students that or we can say the mean ACT score has increased when students complete the recommended courses. Okay. So again, that's our conclusion. We make sure we say, since we rejected H0, that means we do have sufficient data. We mentioned the level of significance, and then we state our H1 claim, which we're now accepting. The mean ACT score has increased. And then we, again, continue with the description of the event. So saying, what does this tell us? Well, when our students completed the recommended coursework, they did get a higher ACT score as a result, which kind of seems like an obvious thing, but it's nice to back it up with statistics. All right. Let's look at one more example, and I think it will be good. I'm going to change the values in this case because the problem 14, the way it's written, comes out to be reject H0 also. I'm going to try to change the values to see if we can come up with a scenario where we fail to reject, so we can at least look at one in that regard. I may or may not be successful in this endeavor. So, anyway. Again, need a new piece of paper. Alright. I'm going to call this problem 14. I'm going to put an asterisk there because I am changing some values. Now, let me read the original problem 14 and we'll go from there. Do students who learned English and another language simultaneously score worse on the SAT critical reading exam? That seems like anyway. Score worse on the SAT critical reading exam than the general population of test takers. The mean score among all test takers on the SAT critical reading exam is 501. A random sample of 100 test takers who learned English and another language simultaneously had a mean SAT critical reading score of 485, with the standard deviation of 116. Do these results suggest that students who learn English as well as another language simultaneously score worse on the SAT reading exam? And the answer turns out to be is yes, which kind of seems obvious again, but again, we like to back these things up with actual statistics and calculations and things like that. But let me see if I can mess with these numbers and come up with something that fails to reject, just so we can see what one of those looks like. So I couldn't find any good problems in the book where it actually came out to be fails to reject. So we have a mean, and I'm going to say that the mean, I'm going to go ahead and keep it at 500. Well, it was 501, I'll just change it to 500. Sample size, it says 100. Let's drop that down to 50 so we create a little bit more uncertainty. And X bar, let's use 490. That should be enough right there. For our standard deviation, the problem gives 116. Let's go ahead and use that. And alpha equals 0.1 level of significance. Let's see if I did enough there to make it fails to reject. But anyway, let's just use these values instead and see where it goes. So basically, I decreased the sample size. I just slightly increased the sample mean, and I slightly decreased the population mean. Making these numbers closer together and making this number smaller puts this more in the realm of possibility that this is just a normal result in the overall scheme. We'll see. Let's state our hypotheses. H0, we have mu equals 500. H1, now notice we got a smaller value than the mean for our sample, so our claim is that mu is now less than 500, which makes it a left tail test. So less than is left tail, greater than is right tail. Alright, so looking at our graph, my normal curves are like fingerprints. You never get the same one twice. So we have a 0.1, which is a little bit larger area. 0.1 level of significance for our critical z-score. So alpha equals 0.1 with that gives us z equals, and for our left tail we'll use negative 1.28. Okay, so we calculate our test statistic ZT, and this is where we're going to find out how successful I was in altering this problem. So we get square root of 50, and then we have 490 minus 500 divided by 116. So put that into the calculator. Root 50 times 490 minus 500, and then divide by 116. Oh, very good. So we get a value of negative 0.61. So we had a little more play. So ZT would actually be somewhere in here, negative 0.61. So we notice now ZT is not in the shaded area. So our conclusion is that we fail to reject H naught. What this really tells us is that with the amount of data that we have at the values that we got, it's well within reason that we could take a sample of 50 people from a population that has a mean of 500, and we could get a sample of 50 where the mean was 490. That's within the realm of possibility because our sigma is large enough and our sample is small enough. So if we had gotten a larger sample with a smaller standard deviation, if either one of those things changed, or the difference between these two was increased, then we might have a little bit more data to go on, which is actually what happens in the actual problem. But how do we write our summary sentence now if we fail to reject? Well, that means we do not have enough data at the alpha equals 0.1 level of significance, which is actually a pretty large amount of error there. So we really did not prove anything with the numbers that I changed it to. To say that the mean has decreased for students that have learned English and another language simultaneously. Now, I don't. That is not to diminish the very real problem of students growing up in a bilingual household that do not have the same level of mastery of the English language as people who have only learned English their entire lives. That's a very real problem. So I don't mean to make light of that here. I just wanted to give an example where it comes out to be fail to reject, just so we can see what that looks like. As a way of comparison to the other two problems where we did reject H naught. So hopefully that was informative. Yeah, realistically, going with the values that are given in the problem, it does come out to be reject H naught because it is an issue. So anyway, especially one that we see around here with students largely of Hispanic descent or Hispanic families, Mexican and otherwise, where you grow up learning both languages at the same time. It does prove to be problematic. I mean, not that it's a bad thing to be bilingual, but it does mean that we just don't have the same level of mastery as students who basically learn English the entire time without learning that second language. Which you kind of expect that to be true anyway. If you're just focused on one language, you should be better at it than someone who's focusing on multiple languages. But again, there are people that do have a knack for language more so than others. So that's another issue. Regardless, I mean, That's what it is. Are there any questions here? Okay. All right. I think we'll wrap it up there. So tomorrow at 9 o'clock, 9 to 11, I'm planning to do a review session for our statistics final. This is the final review that I posted last week in Canvas in the files. And you'll notice that yesterday I posted my key to that review. You will notice on the hypothesis test problem that I used the p-value approach rather than the classical approach. So we may look at that specifically tomorrow just to show it how it works the other way. Anyway, that'll be tomorrow, and you will not be allowed to use notes in the final. All you'll have is the formulas, and you'll have your calculator. You can any calculator, 83, 84, or 36. Yeah. Any other questions? Haley, I don't know. I do have something I'm going to post in Canvas later today regarding the instructions for taking the final, both in person and online. And what it amounts to is that if you haven't, for those of you taking the test online, if you haven't been invited to a Canvas course for that or a conference for that, you should expect to get that soon. And so you'll connect to the conference at the designated time, and basically you'll have to present your ID, whether you have your school ID or your driver's license, something like that, just to prove your identity, make sure you're the person taking the exam. And then basically it's just like going on to a Zoom call where the person on the other side will have like 6 or so people that they're watching, just making sure you all aren't cheating or anything. I don't know that we use a lockdown browser. I still haven't been able to get a straight answer from the people that are coordinating that. It may just be that you just take a normal Canvas test, but it's supervised through like a Zoom call or Teams or whatever it is. So yeah, see if I can find anything else out. It's a struggle at this point. No other questions? Okay. So I do wish you all good luck on the final, getting through the rest of your classes as well. I hope you've enjoyed this semester, and the online learning hasn't been a terrible experience, I hope. No, it's not ideal. I would definitely prefer to be teaching in a classroom rather than over the internet like this, but we do what we have to. Hopefully in a few, another month or two, start getting vaccines and then start getting back to normal. Alright, so you all take care, and again, we'll have a review tomorrow morning at 9. Otherwise, I wish you all the best, and have a good day. Bye.